Welcome to the 10th lecture of my series on vector calculus. The title of today's lecture may seem a bit surprising. It is Reversing the Holy Trinity. As the lecture goes on, I'm sure you will understand what this title means. But below the title, I have written the name of two important theorems, the Uniqueness theorem and the Helmholtz theorem, which we are going to discuss in today's lecture. Let me remind you that we have already derived a bunch of identities which involve these differential operators. They were identities of the first kind where a single one of the operations, gradient, divergence or curl, was acting on a product of two entities. You can see them on your screen right now. We also had identities of the second kind where you had two of these differential operators acting in succession. Now that we have all these vector calculus identities under our belt, as well as the integral identities of Gauss and Stokes, it is time to ask a very important question. We all know that if we are given a scalar field phi and apply the gradient operation on that, we get a vector field. Similarly, if we start with a vector field, we can apply the divergence operation on that to get a scalar field, or the curl on that to get a vector field. But can this process be done in reverse? In other words, if we are given the result of one of these differential operations, can we use that to reconstruct the original field? This will turn out to be a very, very important question in many branches of physics. We will see some examples of that soon. But let us first go on and ask ourselves the questions properly. Can we reconstruct a scalar field from its gradient? Or a vector field from its divergence? Or a vector field from its curl? Or maybe a vector field if both its divergence and curl are specified? Now the answer to all of these questions is slightly complicated. So let us tackle them one by one. First, let us talk about this. Suppose somebody came over to you on the road and said, okay, here is a vector field A, which is the gradient of some scalar field phi. Can you find phi for me? Well, if it is a completely arbitrary vector field that this fellow has given you, the answer is most likely no. After all, if A is the gradient of a scalar field, we know that it must have a zero curl. After all, this is a direct consequence of the identity curl grad phi is zero that we worked out for all smooth scalar fields. So if the vector field that has been given to you by this person doesn't happen to have a zero curl, then you can safely say that there will be no scalar phi whose gradient will give you A. But what if this person was genuine and he had really given you a gradient of a scalar? That is, the vector field that has been given to you does have zero curl. The question is, can you uniquely find out the scalar field phi then? Note that the question is not just whether you can find out the scalar field phi. The question is also whether this answer is unique. Since the gradient is nothing but the del operator, the nabla operator acting on phi, leading to a vector field with components del phi del x, del phi del y and del phi del z respectively, one sure shot approach could be trying to solve these set of equations. Del phi del x is ax, the x component is a vector field given to you, del phi del y is ay, del phi del z is az. If we can solve all of these three simultaneously, then we will find phi. Another, perhaps simpler approach is simply to note that the infinitesimal change in phi, d phi, is nothing but grad phi dot dr, and in this case it's going to be the vector field A dot dr. So if we were to integrate this from r0, some arbitrary point, to the point r, and of course the integrand will depend on a dummy variable which I am calling r prime now. So if you integrate a at r prime dot dr prime from r0 to r, you are going to get phi of r. Now, one immediate question that could arise in this case is when you integrate this differential a at r prime dot dr prime from r0 to r, you have to integrate this along some path. And there are infinitely many paths between r0 to r. So one immediate thing that can come to mind is, even though this phi of r will have a gradient of a of r, is this phi of r at all unique, or do you get infinitely many solutions corresponding to the infinitely many paths which are possible? And the answer to that is again something you perhaps already know. The integral above happens to be independent of the line used to carry out the integration. So there is no non-uniqueness in phi of r coming from this source, that there are infinitely many paths. To see this, just consider a situation where you're integrating from r0 to r along two different paths, gamma 1 and gamma 2. And let's talk about the difference of these two quantities. I've written a dot dr here, but this should really be ar prime dot dr prime, since r is the unique vector which is taken to be the position vector of this endpoint. So let's write it properly. This is going to be a dot dr prime minus a dot dr prime. A, of course, is evaluated at r prime in both cases. But the difference of these two is basically the line integral when you go along gamma 1 like this from r0 to r, and then when you come back along the line traced through gamma 2 but in the opposite direction, back from r to r0. So this really is the line integral of a dot dr over a loop gamma. Now, Stokes' theorem tells us that the line integral of a vector field A over a closed loop is given by the curl of the vector field's integral over the surface sigma. But this is simply curl grad phi dot ds over sigma, since A is gradient of phi according to our proposition, and for every smooth field curl grad phi is 0. So what we end up with is the difference in the two integrals over gamma 1 and over gamma 2 is actually 0, and therefore both of these integrals are one and the same. So the infinitely many possibilities of paths from r0 to r does not give us a lack of uniqueness. However, phi of r really is not unique, and you can see that immediately in this expression. After all, the integration is done up to r, the point where you want to find phi, but it is done from a fixed arbitrary point r0. This point is arbitrary. So if we were to change this point r0 to say r0 prime, the integral for phi r will now become the integral from r0 prime to r, and that of course will be the same as the integral from r0 to r, but to which you have to add a further integral, one from r0 prime to r0. Now note that in this additional integral, which is a of r prime dot dr prime, integrated from r0 prime to r0, there is no mention of the vector r. This integral will depend only on those arbitrary points chosen, but will be completely independent of the position where you want to find the scalar field phi. So this additional piece is just a constant. So what we do see is that this approach tells us that adding a constant to phi of r can always occur. All you are doing here is changing your arbitrary point r0 from which you start the integration. If you look at the other approach, where we solve the equations del phi del x equal to ax, del phi del y equal to ay, and del phi del z equals az simultaneously to get back to phi, there also it is easy to see that ultimately there will always be a constant of integration when you try to solve these partial differential equations. And that constant, since it has zero partial derivative, can always be added to your phi. In other words, gradient of a constant c is 0. And therefore, if phi satisfies grad phi equals vector A, then so does phi prime, which is defined to be phi plus c, where c is an arbitrary constant. It's easy to check that gradient of phi plus c, that is gradient of phi prime, is grad phi plus grad c. And grad c being 0, this is the same as grad phi, that is A. So phi prime and phi will definitely have the same gradient if they differ by a constant function. So, if you are given the gradient of a scalar and asked to find the scalar from it, it's obvious that the answer has to be non-unique, in the sense that you should always be able to add a constant to phi without changing its gradient. And so, phi and phi plus a constant has the same status as far as this particular problem is concerned. Now, one important question to ask would be, is it true that this is the only such uniqueness that this problem has? To answer that, all you need to see is if you had two different scalars, phi 1 and phi 2, with the same gradient, what can you say about the difference phi 2 minus phi 1? It is obvious then that grad phi 2 minus grad phi 1, gradient of phi 2 minus phi 1, will be 0, because grad phi 2 and grad phi 1 are both equal to the vector A. So the phi 2 minus phi 1 you are looking for is actually a scalar field whose gradient is 0. Now it is very easy to see that the only scalar field which has 0 gradient has to be a constant. After all, this scalar field must have a partial derivative of 0 with respect to each and every one of x, y and z, all the three possible variables. So the only possibility is that it does not depend on any one of them, and so is a constant. So in this case, phi 2 minus phi 1 must be a constant. So the non-uniqueness that you have in the solution of grad phi equal to A is only up to a constant. In other words, the solution of grad phi equals A is essentially unique. Essentially, not actually. Because you can always add a constant to a solution and you will definitely get a new phi which also satisfies the equation. By the way, this is a question which is not just important for its mathematical value. This is a question of immense importance in physics. You may already know of a very important situation which arises in electrostatics. In electrostatics, curl of the vector field E is 0, and which suggests that we should be able to write E as the gradient of a scalar. Now this scalar, in keeping with the tradition which has been established already in mechanics, is not called the potential, its negative is called the potential. So E is minus gradient of V. So the question now would be, if the electric field of a system is known, can we figure out the potential from there? And the answer is we can, following the procedure that we just outlined. But again, the potential there would be non-unique, or rather unique up to a constant. If you add a constant to any potential, the physics of the problem will not change because the electric field will stay the same. We often exploit this freedom to choose an arbitrary constant to simplify the expressions at hand. For example, if you were to calculate the potential due to a positive point charge q at the origin, then the potential at a point at a distance r from it would work out to be, using the simple Coulomb's law and the integral that we outlined a while ago, q by 4 pi epsilon 0 into 1 over r minus 1 over r0, where r0 is the distance from the origin of the arbitrary point that we had chosen as a 0 point for phi, the scalar field. Now it's obvious that the expression will become a lot simpler if we choose R0 to be infinity, and that's exactly what we usually do. So this is the reason why in electrostatics potentials are usually measured from infinity, because that will lead to a simpler expression. Let us now turn to a slightly more difficult question. The question of reconstructing a vector field from either its divergence or its curl or both. Now, if the divergence of a vector field is specified, let's say we are given the scalar phi, which is known to be the divergence of A, it is obvious that we cannot solve this uniquely for A, since there are infinitely many vector fields which have zero divergence. A word about the nomenclature here. Vector fields which have zero divergence are called solenoidal. That actually is taken from magnetism, magnetostatics to be precise. The magnetic field is a field with zero divergence, and one of the most common ways of producing a magnetic field is using a solenoid, which is why all zero divergence fields are given this epithet, solenoidal. Now, as I have just said, all magnetic fields are divergence free. And there are, of course, plenty of non-trivial magnetic fields around. So even if you manage to find one solution to the equation divergence of A equals phi, and actually you can, it will turn out that you can add to it any vector field like a magnetic field, which is solenoidal, and the resulting new vector field will also have the same divergence. So, while you can solve the equation divergence A equal to phi to get an A, whose divergence is equal to a specified scalar field, this solution will usually not be unique. What about the curl? If you are given the curl of A, a new vector field B, and you are asked to find A, then your task becomes even more involved. After all, an equation like curl of A equals B is not even consistent unless the divergence of B happens to be zero. This, of course, is another application of our vector identity that we had derived before, that the divergence of the curl of any smooth vector field is zero. Now, if divergence of B is zero, you can actually solve for A. But as for the divergence, this is not going to be a unique solution. There are, in fact, infinitely many non-trivial vector fields which have a zero curl. That is, which is irrotational. That again is another piece of nomenclature. The curl, remember, is related to the rotation in a velocity vector field, and a zero curl vector field is therefore called irrotational, irrespective of what the physical meaning of this particular vector field happens to be. So, neither the divergence nor the curl contain enough information for you to reconstruct the vector field back. It might seem that specifying both the divergence and the curl would be enough for this reconstruction. In fact, many textbooks seem to imply this, especially when they discuss topics like electromagnetism, although very few people actually explicitly say this. And there is a reason for their being silent on this. As you may have guessed, specifying the divergence and the curl of a vector field does not uniquely specify what the vector field is. There happens to be non-trivial vector fields which are both irrotational and solenoidal. If you press for an example, I can immediately quote the electric field due to a point charge at the origin. It definitely has zero curl. All electrostatic fields have zero curl, and its divergence everywhere except at the origin happens to be zero. In fact, we have seen that the inverse square field has a zero divergence in the very second lecture of this course. So, specifying both the divergence and the curl, even that is not enough to uniquely specify my vector field. But there is a very important theorem which actually gives us a positive result in this direction. If the divergence and curl are specified, and these specified fields vanish sufficiently fast at infinity, and this field vanishes at infinity, then A, the vector field, whose divergence and curl have been given, can be uniquely determined. So this is a situation where divergence and curl of a vector field is sufficient to tell you what that vector field is. Now this happens to be the result of a very, very important theorem named after Helmholtz. We are going to discuss the Helmholtz theorem in the later half of this lecture, but before we can talk about that, we have to discuss another theorem which happens to be immensely important in physics, especially in electrostatics. While electrostatics is not really of concern here, we will have to talk about this theorem, the so-called uniqueness theorem, if for no other reason than for the fact that it will be essential in the proof of Helmholtz theorem. In fact, it is perhaps quite fitting that a result which is useful in electrostatics is going to be of importance here. After all, one of the first problems you face in electrostatics is the problem of the determination of the electric field. And the basic equation that is of use here is Gauss' law. This tells us that the charge distribution in a region uniquely fixes the divergence of the electric field there. But as we have already seen, just fixing the divergence is not really enough. However, electrostatics also tells us what the curl of the electric field is. In fact, it tells us that it is exactly zero. So we do know the divergence and the curl of the electrostatic field as long as we know the charge distribution. It is actually Helmholtz theorem which guarantees that if you couple this with the fact that the charge density dies out when you move very far away, because the charges are usually localized in a region and the electric field falls off very fast, that this is really sufficient to tell us what the electric field is going to be. Just the divergence and the curl would not have been enough. You would have to couple it with these boundary conditions. A very similar situation also occurs in magnetostatics, where Ampere's law, the law which governs how currents produce magnetic fields, tells us the curl of the magnetic field. And as we have said before, the divergence of a magnetic field is zero everywhere. So once again, the curl and the divergence of the magnetic field is specified once the current density is known everywhere. And once again, Helmholtz theorem guarantees that this would be enough to calculate the magnetic field at a point uniquely, provided the current dies out fast enough at infinity and the magnetic field itself vanishes at infinity. So let us make a brief detour into electrostatics so that we can motivate the uniqueness theorem. In electrostatics, we deal with a very important vector field, the electric field, the electrostatic field to be precise. Now the electrostatic field is subject to two very important properties. One of them is that its divergence, which essentially talks about the source of the vector field, is proportional to the charge density, the local charge density. Divergence of E is given by rho over epsilon 0. And the other very important result is that the electrostatic field produces a conservative force, which essentially means that the curl of the field has to be zero. In case you have not studied electrostatics yet, and these particular properties are unknown to you, do not worry. We are just using this as a stepping stone towards the important theorem that we are talking about, and in particular, we are going to use this to derive, or rather motivate, a very, very important equation in mathematical physics, the Poisson equation. Now, given the fact that curl of E is zero, we should be able to write E as the gradient of a scalar, and by convention is written as negative of the gradient of a scalar called the potential. So E is minus grad V. Now, Using the fact that divergence of E is rho by epsilon 0, this tells us the divergence of the gradient of V is nothing but the negative of the divergence of E, and therefore it's negative of rho over epsilon 0. So we end up with a very, very important equation in mathematical physics called the Poisson equation. Laplacian of V equals minus rho by epsilon 0. This, of course, is an extremely important equation in electrostatics, because from this, after imposing boundary conditions, we should be able to find out the scalar potential, and the scalar potential is enough through E equal to minus grad V to give the electrostatic field for the problem. Indeed, the Poisson equation actually appears in many other branches of physics. As a result, it is a very important equation in its own right. Now, the homogeneous version of this equation is the one in which the right-hand side vanishes. In electrostatics, this happens when you do not have a local charge density. So, even if you have charges in some other region, but you don't have any charges in the region under consideration, then within that region, Laplacian of V will be 0. And this equation is called the Laplace equation. Now, I am sure you are familiar with one solution of the Poisson equation, at least in a particular situation, even from your high school physics course. If you have a point charge at the origin, the potential due to that at R is given by 1 over 4 pi epsilon 0 times Q by mod of the R vector. Now, instead of having a point charge at the origin, if you have a spread out charge as is described by this charge density rho, it is pretty easy to figure out that a potential which satisfies the Poisson equation is given by this. V of R vector is given by 1 over 4 pi epsilon 0 integral over tau of rho at R prime divided by mod of R minus R prime d cube R prime. Here R prime is the so-called source variable, the location of where the source charges are, and you are actually integrating over this source variable, that is, you are summing up the contributions of all the charges. And this region tau over which this integration is being done is essentially the region where the charges are. By the way, since rho of R prime usually is confined to some region, this integral has to be done over that region, but you can also do it over a bigger region which contains this. Simply because in the additional part that you are including now, rho of R prime is 0. There are no charges in this additional region, and so the integral will not change. So this tau is a region where the charges are, or some bigger volume which encloses the region where the charges are. This could in fact actually encompass all space, at least in the calculation of the potential for the charges that you are interested in, simply because the charges that you are interested in is in some region, and if you take all of space, then this hugely big region that you are taking in addition, in fact the infinitely big volume that you are taking, has no charge density, so contributes nothing to the integral. Before we get all excited and claim that we have managed to solve the Poisson equation once and for all, let us first check whether this is a solution at all. The check is pretty simple. You have to calculate the Laplacian of this V and see whether it does give you minus rho over epsilon 0. Now the Laplacian is a differential operator. This constant 1 over 4 pi epsilon 0 will of course jump out of the differential operator. So you are now left with the Laplacian of this integral. Now note that when you are doing the integral, you are actually integrating over the variable r prime, while you are holding the vector r fixed as far as the integration process is concerned. The Laplacian is actually with respect to the components of the vector r. This has nothing to do with the integration process, and as a result, you can actually first calculate the Laplacian of the integrand and then integrate, as opposed to what is being done here, which is integrate first over r prime and then take the Laplacian. In other words, I can take the Laplacian inside the integral sign, and this leaves you with this particular result, that Laplacian of rho of r prime by mod of r minus r prime needs to be calculated. However, rho of r prime once again is a constant as far as the Laplacian is concerned. Let me remind you once again that the Laplacian involves second derivatives, sum of second partial derivatives with respect to the components of r, and rho of r prime depends only on r prime and is independent of r. Of course, the 1 over mod of r minus r prime is not independent of r, and that is what still has to be taken the Laplacian of. Now, Laplacian of 1 over mod of r minus r prime is something that we had actually already calculated before. After all, it is the divergence of the gradient of 1 over mod of r minus r prime. Remember, that's what the Laplacian is when it acts on a scalar. It is the divergence of the gradient of the scalar. The gradient of 1 over mod of r minus r prime is pretty easy to calculate. It turns out that it is actually a vector in the direction of r minus r prime whose length happens to be inversely proportional to the square of the distance between r and r prime. So it's minus r minus r prime. The minus sign tells you that it's actually against that direction, divided by mod of r minus r prime whole cubed. The cube here, of course, is because the vector r minus r prime in the numerator has a length equal to mod of r minus r prime. So this is really the unit vector in the direction of r minus r prime divided by the square of the distance between r and r prime. R minus r prime mod square. Now, the divergence of this inverse square vector field is something we had calculated in our very second lecture, and had shown that this is a very special kind of function called the Dirac delta function. It's equal to minus 4 pi. The minus is simply because of the minus sign here. 4 pi times delta cube mod of r minus r prime. Remember, if it is in an integration over r prime, the delta function essentially forces all the rest of the integrand to have r prime equals r, and therefore Laplacian of v of r becomes 1 by 4 pi epsilon 0 integral over the region tau rho of r prime minus 4 pi delta cube r minus r prime minus rho of r over epsilon 0. By the way, you might be wondering what happens if my point r, the point at which we are measuring the Laplacian of the potential, happens to be outside tau, the region where the charges are. Of course, in that case, delta cube of r minus r prime will be 0 throughout the integration region, because r prime will only be somewhere within tau and r is somewhere outside, and therefore the integral will work out to be 0, leaving you with a 0 Laplacian. But that is not surprising. Remember, the Poisson equation, the local equation, it talks of the Laplacian of a potential being equal to or being proportional to the charge density at that particular point. If my point r is outside tau, that means there is no charge density at r. Therefore, the potential outside the charge region will definitely have 0 Laplacian. Now this is great. We have managed to solve Poisson equation. But this may seem like a bit of an anticlimax. After all, I have been claiming that the Poisson equation is one of the most important equations in mathematical physics. And here we are, having solved it completely on the basis of the knowledge that we picked up in high school. But just wait a minute. We have found a solution to the Poisson equation. The question is this solution unique? And the answer to that is no. And that is what all this excitement about the Poisson equation is about. As an example, if you had a charge density given by rho of r prime within this orange region here, and this whole charge density was surrounded by a conducting sphere which were connected to the ground, then the potential at a point r in this region would not be given by 1 over 4 pi epsilon 0 integral of rho r prime by mod of r minus r prime d cube r prime over this orange region tau. And it's easy to see physically why that will not be. the charge density here is going to induce a charge on the spherical shell, and this charge is also going to contribute to the potential at this point. And therefore, the problem cannot be solved in this simpler fashion. The answer to this problem, however, this particular problem, is actually still unique. Only it's a way more complicated answer than the one that we had written down before. It's given by something which looks slightly similar. It is actually 1 over 4 pi epsilon 0 integral of rho r prime multiplied by a factor which is way more complicated than 1 by mod of r minus r prime. But it is actually similar in structure to the solution that we had before. Earlier we had 1 by 4 pi epsilon 0 integral over tau of rho r prime by mod of r minus r prime dq r prime. In this solution, the 1 by mod of r minus r prime has been replaced by a more complicated function, 1 by mod of r minus r prime minus capital R by r prime divided by mod of r minus r square by r prime square, capital r prime, and this whole thing is then integrated over r prime. Here capital R is the radius of the sphere, and we have assumed that the origin in this case has been placed at the center of the sphere. So the small r prime that you're dividing by in the numerator of the second term, or the small r prime square in the denominator of the second term, are actually distances of the source point from the center of the sphere, not from any arbitrary origin. Now, you might be asking, why are we so sure that this answer is unique? Of course, another question that might very well have come to you is, how did we come to this solution at all? Actually, the answer to both are very, very connected. The answer happens to be in a theorem which is called the uniqueness theorem. In fact, in electrostatics, the uniqueness theorem gives us a way of figuring out potentials for problems like this. It's a method called the image method, which those of you who have studied electrostatics must have already studied. And the reason why the image method at all works is the uniqueness theorem. I'm not going to talk about that in this lecture. After all, this is not a lecture on electrostatics. But what I wanted to point out is that even in a situation like this, the answer is actually a unique answer. Let us now turn to the uniqueness theorem. What does it say about the solutions to the Poisson equation? Are they unique? If so, under what conditions? To see this, let us begin by assuming that the solution to the Poisson equation in a given region is not unique. There are at least two such solutions. Let's say V1 and V2 both satisfy the Poisson equation. Laplacian of V is minus rho by epsilon 0 for the same charge density rho of R in a region tau. Then small v, which is V2 minus V1, the difference, satisfies the Laplace equation. Because the Laplacian of small v is the Laplacian of capital V2 minus Laplacian of capital V1, and that of course is 0 in this case because Laplacian of V2 and Laplacian of V1 are both equal to minus rho of R by epsilon 0, the same rho of R, remember. Now it is time to make use of the vector identities that we have learned, at least one of them. Let's consider the divergence of this quantity, small v times the gradient of v. The vector identity that we will need here is actually the vector identity involving the divergence of a scalar times a vector field. Here small v is the scalar field and gradient of small v is the vector field. So phi is small v and gradient of small v is a. And the identity that we had was, this is going to be phi times divergence of a plus gradient of phi dotted with a. Now, if you use that here with small v as phi and gradient of small v as a, you immediately get this result. Phi divergence of a becomes small v divergence of gradient of small v, and gradient of phi dotted with a becomes gradient of small v dotted with gradient of small v. Now, the identification that we had talked about at length in the last lecture, divergence of the gradient of a scalar field is called a Laplacian. So this is v times Laplacian of v. And grad v dot grad v is of course the modulus square, the length squared of the vector grad v. Since small v satisfies the Laplace equation, Laplacian v is 0, so this first term goes away, and the divergence of v gradient of v is nothing but gradient of v's mod square. Now, if you have a divergence of a quantity, the identity that you would immediately want to make use of is Gauss divergence theorem. That is, you would integrate this quantity over volume. So if you were to integrate grad v mod square over region tau, so grad v mod square dq bar integrated over tau, that's the same thing as integral over tau of divergence of v grad v dq bar, and this, according to Gauss divergence theorem, will be changed into a surface integral. In fact, a closed integral, because the surface here, the boundary of tau, is surface sigma, being the boundary of a volume, has to be a closed surface. So you have to do v grad v dot ds is integral over the surface, and that's the same as our integral of grad v mod square. Now grad v dot ds is the same as grad v dot n hat ds, where n hat is the unit normal locally to the surface, and grad v dot n hat is nothing but the directional derivative in the direction of n hat of the scalar field v. The rate at which the scalar field v would change if you were to move infinitesimally in the direction given by n hat. That is shorthanded to del v del n. So what we have is that this integral on this side is the surface integral over the closed surface sigma of v del n ds. Now so far we have said nothing about the boundary conditions. We have just said that v1 and v2 satisfy the same Poisson equation for the same rho of r inside a region tau. Now we must begin to think about what is specified on the surface sigma of this region. Since the Poisson equation is a second order partial differential equation, its solutions will definitely depend upon the boundary conditions. Now let's say capital V, the potential that we are trying to find out, or its normal derivative del v del n, is specified on sigma. That is, your problem actually states that okay, rho of r inside tau is this much, and on the surface sigma, v has to be this much. In the case of a grounded sphere example, we knew the charge density inside the sphere. It was inside that orange region in the picture. And the potential on the sphere itself, which was the boundary of the region enclosed by the sphere, happens to be 0. So that was the specification. There, of course, the potential was 0 because it had been grounded. It could have been a much more complicated kind of potential specification if this sphere, instead of being a metallic sphere, had been made out of a dielectric and some kind of potential had been imposed on it. But in any case, the full problem that we are dealing with is not just the Poisson equation satisfied by capital V, but also the specification of capital V or of del V del n on sigma. But if you do that, then capital V1 and capital V2 will both have to match on sigma. Or if del V del n is specified, then del capital V1 del n and del capital V2 del n will have to match on sigma. So either small v, the difference of V2 minus V1, or del small v del n, which is the difference of their normal directional derivatives, will have to vanish on sigma. But when you are calculating the surface integral over sigma of v del n ds, the values of small v that you are going to use are the values on the surface. So if either small v or del v del n vanishes on the surface because of the specified boundary conditions, then this surface integral will have to vanish. By the way, there is one more way in which you can specify the boundary condition on sigma so as to ensure that this particular surface integral vanishes. Instead of specifying capital V all over the surface or del V del N all over the surface, you could even specify capital V over part of the surface and del V del N over the rest. Then small v will vanish over part of the surface. Del small v del N will vanish over the rest. But the integrand will vanish everywhere on the surface, and even then the integrand will turn out to be 0. So in all of these special kinds of boundary conditions, small v will obey this. Grad v mod square dq bar's integral will have to be 0 over tau. Now an integral is a sum, and it can of course be 0 even if the integrand is not 0. But notice that here there is a special thing about the integrand. Grad v mod square is the length of a smooth vector field. In fact, square of the length of a smooth vector field. And this quantity is intrinsically positive. If it were to differ from 0 at even one point, because of smoothness it would have to differ from 0 not only at that point but also in its neighboring region. In fact, it would have to be positive throughout the neighboring region. And that will give a positive contribution to this integral, which will not be cancelled by a negative contribution coming from anywhere else. The integrand here can never be negative. As a result, this integral being 0 actually tells you that grad v mod square has to vanish everywhere on tau. In other words, grad v, the gradient of the scalar field V, has to vanish on tau. And we have seen a while ago that if a scalar field, the gradient vanishes identical in a region, then the scalar field will have to be a constant. Now, if the boundary condition happens to be such that the value of capital V is specified on sigma, then small v has to vanish on sigma. And because it's a constant inside tau and 0 at the boundary of tau, it has to be 0 everywhere in tau. In other words, V2 minus V1 has to vanish everywhere. And so V2 has to be the same as V1. The upshot of all this is, if the potential value V is specified on the boundary of a region and the charge density in the region is known, then there is a unique potential inside that region which satisfies both the Poisson equation and the boundary condition. Things are slightly different if del capital V del N is specified on the boundary. Then del small v del N will have to vanish, and that of course does not imply that small v has to vanish. In this case, all we can say is that the two potentials V2 and V1 can at best differ by a constant. So here the potential is almost unique up to a constant. So this gives us the uniqueness theorem for the Poisson equation. The solution to the Poisson equation in a region is unique if the value of the potential or its normal derivative is specified on the boundary, or even if you have a mixed boundary condition where potential is specified on part of the boundary and the normal derivative is specified on the rest. Now before we go any further, let me point out why this is such a special result. Now in a second order partial differential equation, the second derivatives of the quantity involved comes from the equation itself. What does not come from the equation is the value of the quantity on the boundary. So the value here is not specified as part of the Poisson equation. Neither is the normal derivative, which tells you the rate at which V changes when you go inside the region. Why are we focusing so much on the normal derivative and not derivative along the surface? Because if we specify the value of V on the surface, then its derivative on the surface is automatically given along with that. The rate at which the V changes when you leave the surface, that is not specified when you give the value of V everywhere on the surface. Now, the Poisson equation being a second order differential equation, it might seem that in order to figure out all possible derivatives so that you can move in from the boundary and figure out the values inside, you would need both V and the first order derivatives. As I said, the surface derivatives are already given when you give V. But in addition to that, it might seem that you should also give del V del N. And then that will give you a solution inside. In fact, that is the kind of boundary condition which almost every second order partial differential equation has to have in order to be able to specify the solution. What is so special about the Poisson equation is that you do not need to specify both capital V and del V del N at the same time. In fact, not only do you not need to, you actually cannot. Specifying both capital V and del V del N together would actually over-specify the problem, leading to a possible lack of any solution whatsoever. It is easy to see why that will happen. Since the solution is unique, the moment capital V is specified on the boundary and rho of R is known inside the region, there is a unique solution. Now del V del N calculated on the surface coming from that solution may not match the del V del N that you have specified, and so you will run into a contradiction and hence no possible solution. So, whereas in a second order differential equation you usually need both the value of the variable and its normal derivative to be specified as boundary conditions, for the Poisson equation you need to specify only one of them. The other one can be then determined from the solution which uniquely follows from the problem. By the way, del V del N, at least in the electrostatic context, has an important physical meaning. Remember, the gradient of the V is actually negative of the electric field, and therefore del V del N is nothing but negative of the normal component of the electric field. So put in more physical language, if you have the charge density everywhere in the region, and if either the potential or the normal component of the electric field is specified on the boundary of the region, then the potential inside is essentially unique. Unique if the potential is specified on the boundary, and unique up to a constant if the normal derivative is specified. By the way, the normal derivative cannot be specified arbitrarily either. You have to realize that if you were to integrate the normal derivative del V del N over the surface ds, that's nothing but integrating gradient of V dot n hat ds over the surface sigma. And using the Gauss theorem, we see that this is the integral over the region tau of divergence of gradient of V d tau. Divergence of gradient of V is of course the Laplacian of V, which is specified by the equation itself. So this has to be equal to the integral over tau of minus rho over epsilon 0 d tau or dq bar, and therefore this is going to be net charge inside by epsilon 0 with a negative sign. So when you specify del V del N on the surface, you have to be careful. The specification has to match this result, which comes from the fact that charge density inside the region is already known. So there is a constraint on this specification. If this constraint is violated, once again you get an inconsistency and there will be no solution. Now, a very special case of this is one which will be useful for the Helmholtz theorem. If the only charges that you have are confined to a finite volume tau, and the potential is known to vanish at infinity, then the uniqueness theorem tells you that one solution that you have already verified, and which does vanish at infinity, because rho of r prime is only confined to a small finite region, and when you are at infinity, this is really like d cube r by r's integral over a finite region being done in the limit r goes to infinity. And that, of course, goes to 0. So the uniqueness theorem tells us that this solution is going to be the unique solution to the Poisson equation Laplacian of V equals minus rho of R by epsilon 0. But the condition here is that the potential must vanish at infinity and the charges be confined to a finite region. Of course, if the charges are confined to a finite region, the integral tau can be done over that region or over all space, because the rest of the region will contribute nothing to the integral. Now, our specification of the Poisson equation was somewhat biased towards electrostatics, and that is why you had this minus rho of r by epsilon 0 on the right hand side, where epsilon 0 obviously is a constant which comes in the theory of electrostatics or electromagnetism in general, and rho of r prime is the electric charge density. In general, if you have an equation like Laplacian of phi is given as minus f of r, where f of r is some specified scalar which vanishes at infinity, and phi is also demanded to vanish at infinity, then there is a unique solution to the Poisson equation. And this solution happens to be phi of r is 1 over 4 pi integral over all space of f of r prime by mod of r minus r prime d cube r prime. This is an equation that will be very, very important in the proof of Helmholtz theorem. By the way, there is one very important caveat that we must mention here. All of this makes sense only if this expression for phi of r actually gives you a finite result. And for this to happen, f of r prime must fall off to 0 sufficiently fast at infinity. Merely vanishing at infinity will not be enough. For example, if f actually went as 1 over r prime, then when you are infinitely far away, this quantity will essentially look like an integral of 1 over r prime square over d cube r prime. And since d cube r prime's volume element infinitely far away will be like the volume of a spherical shell between r prime and r prime plus dr prime, namely 4 pi r prime square dr prime, you will have an r prime square in the numerator as well as the denominator. As a result, shells which are infinitely far away will all contribute equal amounts or roughly equal amounts, and they will add up to an infinite contribution. So f of r prime vanishing at infinity is not enough to ensure that this particular integral converges. For that to happen, f of r prime has to vanish sufficiently fast. If it vanishes as r prime goes to infinity as fast as 1 over r prime square, then the convergence of this integral is guaranteed, and so we can truly say that you have a unique solution in this case. Now that we have the uniqueness theorem in our belt, we have all the tools necessary to prove Helmholtz theorem. However, the proof is a bit lengthy, and I will not attempt to complete that in today's lecture. Today, let me just end by giving you a full statement of Helmholtz theorem and one of its very important consequences. Now, the statement of the Helmholtz theorem goes as follows. If the divergence d of r and the curl c vector of r of a vector field f of r are specified, and if they both go to 0 faster than 1 by r square as r goes to infinity, this is being said about d of r and c vector of r. And if on top of that, f of r itself goes to 0 as r goes to infinity, then f of r is unique. That is a theorem. But it actually does not just end there. The theorem actually gives us a way of constructing this f of r from the divergence d of r and the curl c of r. And the equation which helps us do that is the following. Now this equation may look a bit complicated at this stage, but I would like to point out that what is being said here is f of r is essentially gradient of a term which involves the integral of d of r. And in fact, this particular integral may not be very unfamiliar in the light of what we have seen a while ago. After all, this is exactly the kind of expression you get when you try to solve the Poisson equation. And indeed, you have a very similar term involving C of R, which of course gives you a vector field after the integration, and a curl of that has to be taken. Now let me point out one thing. This term, the first part of f of r, is the gradient of a scalar field. The scalar field itself being given by an integral involving the divergence d. Being a gradient of a scalar field, this part has zero curl. So, in the standard language that we use, this is called an irrotational vector field. On the other hand, the other part is a curl of a vector field. And because it's a curl of a vector field, its divergence is zero. So this is a solenoidal field. Indeed, another way of stating Helmholtz theorem would be that every vector field which vanishes rapidly enough at infinity actually is composed of an irrotational part and a solenoidal part, and this decomposition into the irrotational and solenoidal parts is unique, once again, as long as the field dies out at infinity. Now the proof of this theorem is slightly long, but it essentially uses the ideas that we have already talked about. The uniqueness theorem in the context of Poisson's equation. We are going to take a look at the proof and some detailed applications of this in the next lecture. Bye till then.